Hello, good evening, sir. Let's wait for a couple of more minutes and let others join. Then we'll start. Hello, good evening, everyone. Once again, I think we can start now. Hi, my name is Omer Hussain. I'm a PhD scholar in the Department of Mechanical Engineering at IIT Madras, and I'll be taking your doubt session for the course Basics of Finite Element Analysis Part 2, which is a course under the NPTEL initiative. And in these doubt session, we usually discuss the course content of the current week and discuss the doubts regarding them. So the course this course is a continuation to the its previous part one course, which covers the basic aspect of finite element analysis, and then we take move on with that is with those aspect to further more topics in FEM. We started with the error estimation, and then we moved on to numerical integration. We studied various type of numerical integration rules like trapezoidal rule, Simpson's rule, Gauss quadrature, and Newton-Cotes quadrature methods. So last week we finished the Gauss quadrature method and Newton-Cotes method, and then we started on to the new topic of this course, that is 2D finite element method. So we did an introduction in the last week, and then we started with 2D FEM again in this week. So in 2D, the governing equations look something of the form shown in this equation A here. So we have now we now have the second order derivative term in terms of x as well as in terms of y as well. So this is a general equation. Sorry. So if this is a general equation, if we consider a specific form of this equation by assuming certain constants in certain way, we get this equation here B, which is a famous equation to model various type of natural phenomena such as heat conduction, which is known as the Poisson's equation. So right now we are starting with only 1 degree of freedom problem. So it's a one variable problem in 2 dimensions. So just like in the usual FEM, similarly in 2D FEM also we start with the same steps. We start with discretization. So now discretization in 2D FEM is rather a complicated task compared to the 1D FEM. So in 1D FEM we usually had a line as the domain. Not usually, it's always a line as a domain, and to discretize it we had to break this line into smaller elements. So x equals to a here, x equals to b, and in this range we just have to break it into smaller number of elements. So we have 3, 4. So it's not a very big task to break it into 5 different elements. However, in 2D FEM, the geometry can be really tricky and complicated, just like this one shown here. So now, since we know all the different functions and their derivatives in terms of standard polynomial elements, so we can't just break any geometry in any type of random geometry. So what we do mostly is that we choose certain known polynomials such as a triangle or a quadrilateral, and try to fill that random geometry with those shapes. So here I did it using these triangles. So I have this element 1 here, element 2 here, element 3, element 4, element 5. If we can also do the same using quadrilateral elements. So we have element 1, element 2, element 3, element 4, 5, element 6, element 7. So we mainly basically uh, divide the 2D domain into simpler known polygonal elements. So, however, the problem here lies in the fact that we cannot sorry we cannot exactly map that geometry using the standard elements. We are left with we leave some space, or we just over cover some space like one here. So it's never perfect fitting of using the known polynomials. So this includes some one of the errors, that is the error due to imperfect approximation, that we studied in the topic when we are studying various types of errors in FEM. So anyways, we move with that. So this there's a way to reduce this error is to discretize the domain, especially in the area there where there's a high curvature in the domain. So if we discretize more, we reduce the error. Then the next step that is involved our FEM solution is forming the weak formulation using or basically this weak formulation is basically minimizing the error or residual using the weighted residual method. So if we have so we have this equation, Poisson's equation here, and if we fit if instead of we don't know the exact solution, of course we approximate it using some phase shape function. So if we use this approximate solution UH here, we will never get it the left hand side equal to 0. There is always bound to be some error using our approximated solution. uh, so what we basically do is uh, we multiply this residual or error by some weight function and integrate it over the entire element. So this way we get the weighted residual as 0. And the next thing is we weaken the differentiability. That's a concept that we have studied in the 1D FEM. That's not a new thing. So basically, can anyone tell me why do we weaken the differentiability? How is it helpful to us? So it's just a basic revision of the concept that we studied earlier. Can someone answer this? I hope I am audible to everyone, right? You can unmute yourself to answer, or you can type it in the chat. I'll just repeat my question. I was asking why do we weaken the differentiability requirement in our FEM problem?
To meet out the continuity requirement.
Continuity requirement. Yeah, in a way that is right. Seems right. Yeah. So to meet our continuity requirement, while having to choose lower order polynomials, that would I think complete the answer. That was the right answer. So thank you so much. So yeah, so if we have a weaker differentiability, we can just go on with the lower order polynomials as our approximation functions, and that would meet our continuity requirements. So then in 2D we have the 2D form of divergence theorem. That's simply to uh, do the integration by parts and convert uh, our integration over the volume and transfer it to the boundary uh, of the domain. So if you have any doubts anywhere, please you can stop me and ask. I'll try to answer it. So again, So in our FEM problem, okay, yeah, we have the weak form of this type we here where we get a boundary term. So this whole term here is specified is an integral over the boundary of the domain. So the whole term is here. So we know that W is the weight function, and if we specify okay, so yeah, so W is the weight function used primary variable. So if in our problem we're specifying U, that is the dirichlet boundary condition, and if we're applying the value of this term in the boundary term, that is the Neumann boundary condition. So yeah, though, so this is our secondary variable in the problem. So that is basically the 2D form of what we studied in 1D FEM problem. It's the same, except now it's a projection of vector in the normal the direction of the normal of the boundary of domain. So again, our weak form here we can similarly write it in terms of a bilinear and a linear term. So our bilinear term here is this term here. So it's linear in terms of both u and w. That's obvious. Uh, yeah, the constant have to be independent of u, of course. And then it's symmetric only if a12 is equals to a21. So it's not always symmetric in this case, as we can see here. So and again, this is our next is our linear term here, which is linear in terms of w. You don't have any u here. So next thing is to develop the element level equations using our weak form. We assume a solution in terms of the nodes and the approximation functions, the nodal values, and multiply by the approximation functions. So now choosing the approximation function again, we have so in 1D FEM we only used to have only 1D element, right? We can just change the degree of the shape function and have more points defined inside. So here we'll get linear shape functions. Here we'll get quadratic. We'll get cubic shape approximation functions. But in 2D we have an option of choosing various types of elements. So if we can have simple triangle, can have any quadrilateral, and even pentagons. We can choose various complicated geometries, not complicated geometry, but higher, more number of sided polynomials. But we don't usually do that. That's a I think a more specialized branch of FEM that is known as the polygonal finite element. We're not dealing with that here. So yeah, again, even within these functions, we can have linear shape functions, linear approximation functions, or even quadratic or cubic approximation functions based on the number of points we are defining inside. So now we have, so suppose we are choosing the approximation functions for a triangular element. So the most important condition that an approximation function should satisfy is this. So if we are defining the approximation function for node 1, it should have a value of 1 at node 1 and it should go down to 0 at the other nodes. We had some similar problem in I think week 2 or 3 assignment where we were given a triangle and the equation of the sides, and from that we had to derive the approximation function for each node of the triangle. So never mind. We approximate a solution in form of the displacement values or nodal values of the variable and the approximation functions, and we put it into the our weak form. So we can separate out our, in case of simple linear FEM, we can separate out our the derivatives of the shape functions or the approximation functions in separate matrix in K here, and we which is multiplied by this vector uj here, and we can simply write our linear system of equations in this form. I hope, yeah, you guys can recall it. We did this same thing in 1D FEM. Uh, Only our equation is different, so we have more number of terms in K here. The rest all we rest all the everything is same. Type of equations are again linear equations. So next thing is how do we get the interpolation function in 2D? So we know that we approximate the solution in terms of the nodal values and the approximation functions. So we have certain conditions to choose the interpolation functions or the approximation functions in 2D. Again, the final solution should be, so the final approximation UE should be sufficiently differentiable given the differentiability requirement of the weak form. And of course, UE should be a complete polynomial. So if it is more towards the side of uh, any of the any of the uh, any of the dependent variables of the approximation, there's bound to be some error. And of course, the all polynomial terms here should be linearly independent. So we'll see, we considered certain type of elements and certain type of approximation function, which, and for which of the elements would they fit. So suppose if we are taking only, uh, we want only this type of function here. First of all, it should be a a complete polynomial. So we have a 0 degree term and we have 1 degree term. So we have both from 0 to 1. We are not missing anything in between. The second thing is, so what type of element should be used for it? If we have to fit this, so we, of course, if we have three constants C1, C2, C3, to find them, determine these three constants, we need at least three nodes. So if we take a three node element in this form here, so here the system of equation would become linearly dependent, since one of the point is lying on the line of is so we can say that point 2 is like a linear combination of point 1 and 3. So this would we'll see later how this would cause a problem. So for now, this is not correct. So we go with this type of element. So we for three noded for a type of approximation where we have three constant, we take a three noded triangle. Next is if we increase one more term. So then we have so of course we have four constants. Then we need to have four nodes. So again, we can't fit it in a line. And even in a triangle, if we have one or two centroid, that won't work. So we have to go with a quadrilateral. Next is the quadratic incomplete polynomial. So this again we found that is not a valid element. If we have want a quadratic, we can have this type of triangle. So it's a quadratic triangle with next six nodes in it. So these were different types of approximation we could have taken. So we'll start with the simplest subtype of approximation with only 0 and 1 degree term. So how do we derive its approximation functions? So we have a triangle. It's and we know the coordinates of its three nodes. So we want to approximate a solution this way, right? And we know that We can also approximate the solution like this. So if we find the values at the three nodes, so the solution at node 1. So remember this condition. So if we have psi I at x j y j, we get it equals to delta I, right? So if we choose UE at some, say, x1 y1, we should get u is the psi 1 term equals to 1. At this point we have psi 1 equals to 1, psi 2 equals 0, and psi 3 is also equal to 0, right? So what we'll ultimately get solution is u1. So that's and again, if using the first equation here, we get the right hand side of this equation. So likewise at other three nodes, we can get three equations like this. So if we write it in the terms of this matrix, uh, so right now we have u1, u2, u3, defined in terms of c1, c2, c3. But we need to find c1, c2, c3. That's our main task, to find the approximation functions. So we know we if we write in terms of matrix, we have this matrix A here, and to write the equation in terms of to find write the equation to get c1, c2, c3 in terms of u1, u2, u3, we need to find the inverse of this A. Okay, so of course this matrix should be invertible. So that is the reason we need to carefully choose our element. If it would have been uh, say three nodes in one straight line, this matrix A would not never have been invertible. It would have it would have its rank lower than the order of this matrix, and we won't be able to find the value of C1, C2, C3. So that is the issue of choosing a specific type of elements over the others. Yeah, and also in this slide that we can't. So this type of approximation is wrong, right? We can't choose it. So in the light of the same thing, if we have certain type of element where like this, we don't have much distinction between these two nodes. So these geometry would also cause some numerical issues. So A would be theoretically it would be invertible, but the values of inverse would be very rough, some very high values. So it would cause numerical instabilities in our problem. So that's why we prefer to avoid such geometries. So again, so if we take inverse of the above A matrix, we get something some solution like this. And so we don't need to go into much detail of this. Finally, we get the approximation function of a simple triangular element, three-noded triangular element, as these three nodes. So I think that was all for this current week's content, week 5. And if there is any doubt till here, I will try to address it. You're free to ask. Otherwise, we'll move on to the problem solving session. Okay, so is there any doubt? Otherwise, start with the problem solving. Sorry. Okay, then we start. So, so since we are dealing with 2D problems, so we have the gradient and divergence term coming up here and then. So it would be a nice idea to just revise the basic concept of this. So here we need to find the gradient of a vector u and the divergence of its gradient. So in the first problem we have u equals to 2xi plus, right? So what is gradient of u? So we know this del operator is dou by dou x I cap plus dou by dou y of j cap, right? So we just write this. Okay, I think I framed the problem incorrectly. It's yeah, so it's basically yeah. Please go ahead. Okay, so so basically, gradient of a scalar is a vector, and gradient of vector is a tensor.
গরু একেবারে গরু 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 হচ্ছে একটা
So
তৈরি
please
হচ্ছে
unmute yourself.
দেখবো যে তুই কতক্ষণ পড়াশুনো করিস সেটা আমি একটু চেক করে নেই আর বড় বড় ডায়লগ দেয় যারা তাদেরকে একটু চেক করতে হবে হঠাৎ হঠাৎ চিৎকার করে ওঠে
Okay, yeah, unmuted now. So right, so we have dou by dx of ux and dou by y of ux, then dou by dou uy by dou x and dou uy by dou y. So get something like this. So if we have for the partial derivative of the x component with respect to x would be 2, and for y it should be minus 2xy. Sorry, it should be 0. And for y we have minus y square, and here we have minus 2xy. So this is what the gradient of vector u should look like. If you want to find its dot product, we'll try with doing this. So now we want to find this. So we have dou by dou x of 2 is 0 plus dou by dou y of minus y square, we get minus 2y, right? And again, for the next column we have 0 again plus minus 2xy, 2x. Yeah, so this should be the divergence of gradient of u. Fine. So again, if we have for second part, we have u equals to x square y I cap, or we'll just write in terms of vector. It's easier to understand. Square y xy square. So gradient of u is, we'll take the derivative of first term with respect to x, we get 2xy, with respect to y we get x square, we get here y square, we get here again 2xy. Fine. And next is we get the divergence. That would be so we have the first derivative as 2y, then plus 2y again, get 4y, and then again we have 2x, and then again 2x, so we have 4x, get 4 times x, or we can just write it as 4x I cap plus 4y j cap. Similarly, we could have written this term also, minus 2x I cap plus y j cap. The final solution for first part, second part. So I hope this was clear. If there is any doubt, you can ask now. I'll just check while you guys, yeah, you can unmute yourself. You turn on your microphone. There's no doubt, then we'll move forward. Okay, so we need to find the weak form here. So we'll try to break it into its component form. So if we want to break this down, we can write it as Further, we take the dot product. We have dou by dou x of a times of dou t by dou x. So we have dou by dou y of a times dou t of dou y, right? So our weak form would, so our strong form in terms of its component would be, so now we write its weighted residual statement. So we integrate over the element, multiply by weight function. We have, so now we do the integration by parts on the first and second term. We'll have right. And we have the boundary term. So we have to be careful about this W times and the other term. Okay, so these would be our boundary terms. So this is our bilinear term W and T. This side is our linear term of W. Okay. So is there any doubts here? Okay, so if there are no doubts, we can move forward to the next question. So now we have the strong form of this kind. We need to find its weak form. So first thing is take the weighted residual statement. There's something wrong here. Yeah. So there's no minus sign here and here. There's a typo here. Okay, so the next task is to take to do integration by parts. So we transfer the differentiable to W. Dou W by dou X times dou U by dou X, plus we have dou W by dou Y to K times dou U by dou Y. Then we have dou W by dou X times dou U by dou Y. And what would be our boundary term? We have W here. For first term we have dou U by dou X. Then for third term we have uh, dou U by dou Y to X. And then we have our F term, actually minus, it's whole equals to 0. Okay, I think this is clear, right? So we then rearrange the terms. So can someone tell me what would be the bilinear term and linear term here? I'll write. Meanwhile, someone can answer this. Uh, what is the bilinear and linear term here? Okay, so please point out what would be the bilinear term and linear term. So we have this term is linear for W and U, fine, and this term is linear for W. Okay, I have one more question. So is this matrix B, uh, is it symmetric or not? Will it be symmetric? Can someone answer this? Will this bilinear term here is symmetric or not? Can it be symmetric in any condition? Can someone guess an answer? It's a simple yes or no. Okay, so we're not getting response, so I'll answer this. So if to check symmetry, we just have to replace W with U and U with W. So if we have this, take a look at this first term. So here if we interchange W and U, we'll it would appear same, dou w by dou x, dou u by dou x. Here also, we do this interchanging, it will be same, dou w by dou y, k times dou u by dou y, it's same. But however, if we interchange this term, here it's no problem, here it's no problem. But if we interchange this term, dou w by dou x into dou u by dou y, if we interchange, we get dou w by dou y, dou u by dou x. So it's changing the term here. So we don't have symmetry. Fine. So earlier you would have noticed that in a general expression we had two terms for this, like this. So if we had same constant for that, equal constant, it would become symmetric. All right. Okay. So if there's any doubt, you can let me know now, or we can move on to the next problem. Okay. So we need to derive the element level equation for problem 2 and 3. So we had reached to the weak form, right? So we'll start with problem 3. It's yeah. So we have problem 3. We have the weak form. So I'll just not. Okay, I'll have to write because it would cause confusion later. So I'll just repeat this. Okay, so how do we move ahead from this? We approximate US in terms of the approximation functions. So we have some approximation function xij is function of the space coordinates x and y, and yeah, we can approximate this u as here, or for simplicity we just write this as this u just ij. So by default, using Einstein summation convention, it actually means summation here, and instead of, in place of w, we can just substitute by the same weight function, since we are using the same type of approximation function both u and w. So I'll just substitute these terms here back here, the weak form. And here instead of repeating this term, I'll just write it as q. So we have psi I times q plus we have psi I times f. Okay, so here the UJs are independent of space coordinates, so we can just substitute them out. We can sorry pull them out of the derivative terms. We have this omega a left with dou psi I by dou x times dou psi j by dou x plus k times dou psi I by dou, sorry, it's dou y times dou psi j by dou y plus dou psi I by dou x times dou psi j by dou y. So you can pull out the uj term here, right? And again we have this expression here. Okay, so this whole term here is our stiffness matrix Kij. This is our unknown uj. This is our right hand side vector phi. So we can write it like this. This cross implies multiplication, of course. So this is how the element level equations for this kind of problems weak form would look like. So is that clear? So this is fine. We'll move on to the next part of the problem. So we did it for problem 2. We have to do it for problem. We did for problem 3. We have to do it for problem 2 also. So let's see if there's a way to. So copy, can paste it here. Yeah. So we have this term. Let it more clearly. And then we have the other term. Yes. And we just straight away write the boundary term. So like this. Okay, so we again approximate the solution T here as Tj psi j, and we approximate W as psi I. So we substitute this term in the weak form. Dou psi I by dou x a times dou Tj psi j by dou x, dou psi I by dou I a times dou of Tj psi j by dou I. Here on the right hand side we have, instead of w we write psi I times x square plus y square d omega plus psi I times q. Okay, so since Tj is independent of space coordinate, we can bring it out of the integration term. So we are left with dou psi I by dou x a times of dou psi j by dou x plus dou psi I by dou I a times of dou psi j by dou y. Here we have our Tj. Okay, so on the right hand side, simple psi I x square plus y square psi I cube t gamma. Excuse me. So again, so now this term is our matrix Kij. So this is again our solution vector Tj, and on right hand side we have our right hand side vector Fi. So we can write the element level equations like this. Okay, so this is the same way we did the previous problem. So if there's any doubt, you can ask now. So I have a question again here. So will this matrix Kij, is this symmetric or not? Can someone answer this? Anyone? Any guess? So here again, we have two terms in a different matrix. Why? Oh, right. Yeah. So we have this term 1 here, this term 2 here. So in first term, if we replace psi I by psi j, we left with the same terms. The expression looks the same. And second term again, if we replace these two, psi I by psi j, it would again be same. Dou psi I by dou y into a times dou psi j by dou y. Same. So here the matrix Kij now is symmetric. Okay. Okay. So I hope this concept is clear. It's pretty basic concept. So we can move on to the next problem now. So I would need someone to answer these. I'll wait for you to see this and you can answer these as yes or no for each option. So are the following polynomials complete or not? So we have to answer yes or no. Or in case of no, we have to complete these. I'll wait for someone to answer. You can also type in the chat box. Okay, so I haven't received any answer yet. So I'll try to solve this myself. So in option A, we have the polynomial 5x, 5 plus 2x. So will it be complete or not? So it depends on type of problem we're dealing with. If it's in 1D, it's yes. But if we are dealing with 2D, it is no. So for 2D, the complete polynomial should be 5 plus 2x plus some constant times y. Okay. Then we have in this the next B part we have xy plus x minus y. So now we know it's a 2D problem. There's no it's a 1D problem. So and here again we have missing y term here. You can write xy plus x plus some constant a times y minus 1. And then we have 2 plus 3x plus 6y. We miss again a y term here. 2 plus 3x plus 8 times y plus 6xy. This term is complete. This polynomial is complete. 3 plus x plus y plus 5x. Okay, so I hope this was clear. If there's any doubt, you can let me know. Okay, so we can move on to the next problem now. So we have to show that the following matrix is non-invertible by looking at the elements, and then we have to verify the claim using the determinant. So how do we prove a matrix to be non-invertible? Can someone answer this? Okay, so basically there are different ways to check this. Basically, we check the rank of the matrix. If it's equal to the size of matrix, it is invertible. Otherwise, not. There are different ways we to do that. We even there's a common way to write the echelon form of the matrix, and then we the total number of non-zero rows or columns gives the rank of the matrix, and we check if it's equal to the order of the matrix or size of the matrix or not. So basically, by just looking at the matrix, we can check if mm, so we just have to check that the rows and columns are linearly independent. What does that mean? That we can linearly dependent means we can take any two rows and form a linear combination of two rows or columns, form a linear combination of those two, and get the third row or column. So that makes it linearly dependent. If we can't do that, that's linearly independent. Okay, so can someone just see and tell me that if it looks to be appears to be linearly dependent or independent? So it's we have to show it's non-invertible, so you know it's there would be rows or columns that are linearly dependent. So can you identify these? Okay, so anyone, any guesses? So if we see the rows of this matrix, mm, we consider the R1, R2, R3, and we check, we perform 5 times R1 plus R2. What do we get? So 5 times R1 is 115 plus 0 to 1, get 5, 5, 25 plus 0 to 1. What do we get here? 5 plus 0 is 5, 5 plus 2 is 7, and 25 plus 1 is 26. So we get it equals to R3. So that makes the rows to be linearly dependent. Hence, this matrix would be non-invertible. So we can verify this using the determinant. So how do we take determinant? 1 times 2 into 26 minus 7 into 1 minus 1 times 26 into 0 times 5 into 1 plus 5 times 7 into 0 minus minus 5 times 2. So what we get here? 26 2 3 2 minus 7 minus minus 1 times minus 5 is plus 5. Then we have plus 5 into minus 10 makes minus 50. Okay, so we have 52 minus 7 plus 5 is minus 2, then 52 minus 2 is 50, 50 minus 50 is 0. So hence the determinant 0. So that verifies our claim that this matrix is non-invertible. So now think it would be easy to relate how this rows of the matrix, the columns of the matrix becoming linearly dependent makes the determinant 0. Okay, so is there any doubt here? Or we can proceed. Okay, so the next question here is we are given the vertices of a triangle. We need to find the linear interpolation function for this triangle. Okay, so we have triangle whose first node is 0 0, then its second node is 1 0, and third node is 0 1. So this is what our triangular element should look like here. Okay, so we'll try to use the same approach we did earlier. So we have u can be written as summation of or u1 psi1 plus u2 psi2 plus u3 psi3, and so this is approximate value of u for the element. And since we are using three node triangle element, we can also approximate this it as this. Okay, so again at uh, node 1 we have, so from first equation we get u equals to u1, and from second equation we get u equals to, so at node 1 we have both x and y equals to 0, we can directly get c1. And at node 2 we have from first equation we have u equals to u2, and here we have c1 equals to, sorry, x for it's node 2 x equals to 1, we have c1 plus c2, and y is 0, don't have c3, sorry, c3. And at node 3 we have from first equation u equals to u3, and from second equation we have u2 equals, we have u equals to c1 plus, here x is 0 and y equals to 1, we have c1 plus, so we have three equations here, we can write it in terms of that matrix form. So for first row we have coefficient of c1 is 1, and coefficient of c2 and c3 are 0. Coefficient of, in second equation we have coefficient of c1 is 1, c2 is 1, and here c3 is 0. Then for third equation we have coefficient of c1 as 1, coefficient of c2 is 0, c3 is 1. Okay, so this is our matrix here, 1 0 0 1 1 0 1 0 1. Okay, then how should we proceed from here? We can take its inverse, that's, that will take some time, or we can just, since the equations are so simple, we can, maybe I'll try if we can directly solve for c1 c2 and c3. So we know that c1 equals to u1, and from second equation we can substitute c1 as u1 plus c2, so this gives us c2 equals to u2 minus u1. And then we have in third equation we similarly we can write c1 as u1 plus c3, so we can get c3 as simply uh, u3 minus u1, right? So we got the constant value for three c1 c2 c3, three constants. So we, now if we substitute this back into our equation, so c1 is u1 plus Then C2 we can write it as U2 minus U1 x plus C3 we can write as U3 minus U1 y, right? So if we try to arrange these terms in terms of U1, U2, U3, so first for U1 we have 1 minus x minus y. Then with U2 we have only x, and for with U3 we have only y. So if we compare this equation 3 with equation 1 here, we can see that the coefficient of u1 here is in equation 1 is psi1, and here is 1 minus x minus y. So that makes psi1 equals to 1 minus x minus y. Then the second term in equation 1 we have u2 psi2. So coefficient of u2 is psi2, and in equation 3 the coefficient of u2 is x. So psi2 is equals to x. And then third term in equation 1 we have coefficient of u3 as psi3, and equation 3 we have the coefficient of u3 as y. So psi3 equals to y. So for this type of triangle, simple right triangle having nodes 0 0, node 1, node 2 as 1 0, and node 3 as 0 1, these would be the approximation or interpolation functions. Okay, so I hope this was clear. If there is any doubt, you can ask. I'll wait if there's any doubt here. This was a tricky question. It's a new concept, so I think that this would help in understanding how we derive the interpolation function for 2D elements. Okay, so if there are no doubts, we can move forward. So this was a problem in the assignment. I picked it up. So we are given a strong form. So this is actually not a strong form exactly. This part here is the strong form, and this whole thing is the weighted residual statement. So we need to find the differentiability of W, the least differentiability of the W to ensure continuity. So would anyone like to give it a try? I'll just write it meanwhile. Okay, so this is our weak form. So if we want to guess what should be the differentiability of W right now, anyone? So right now there's no derivative term on W. So even if we consider it to be a constant term, we'll be good to go. There won't be any continuity problems. However, these F1 terms, these are F1 means dou u by some constant time dou u by dou x plus some other constant time dou u by dou y. So we'll have this would give us some second order derivative term of dou u by, so say dou x square or dou y square, whatever. So here, so if we choose this w as constant, we would need to choose u as at least second degree term, second degree polynomial, right? So usually, here we would have to choose different type of shape function for w and q. However, we usually use the Petrov-Gelakin method, where we choose similar shape function for similar approximation function for both w and u. So so for that, it is better to transfer the differentiability from u to w. That's why we write the weak form. So we can write this as dou w by dou x times f1 plus dou w by dou y f2, then we have the boundary terms. And the rest of the terms. Okay, so so here in the other terms, here w doesn't need any differentiability requirement. We can just use a constant function, but here we have derivative with respect to w. So now it's a only a first order derivative. So linear function would be fine for it. And again, F1 also we'll have only first order derivative, dou e by dou x, dou u by dou y. Here also again can use a linear function. So at least these should be linear functions here. Okay. So if there's any doubt till now, you can ask. Okay, then we'll move on to the next problem. Okay, so we have another problem for this from the assignment. Which two-dimensional element is suitable for developing the interpolation functions for displacement u, which is given in the form of this function here. U equals to c1 plus c2x plus c3y plus c4xy. So based on the function, can someone guess how many noded elements do we need? How many nodes should be there in the element? Any guesses? Okay, so since we are given four variables, right? Four constant, four unknowns here. This implies we need four nodes, right? So how do we arrange the four nodes? So number one is a very simple thing. We arrange the all four nodes in a straight line. 2, 3, 4. Okay. So would that be a valid element? Can you check this out? Suppose we just mark the coordinate as 0, 0, 1, 0, 2, 0, 3, 0, and we try to write the displacement in terms of the constants. We have at node 1 we have u equals to u1, and another way u can be written as c1. And at node 2 we have u2 and x equals to 1. So we have c1 plus c2 plus, oh sorry, the other terms are 0, y is 0. Again we have to write u3. At node 3 we have c1, again c x equals to 2, so we have uh, sorry, it's c2, 2 c2, and again we don't have any c3 and c4 terms, so it's y is 0. At u4 we have c1 plus 3c2. So now if we try to arrange this system of equations into matrix 1, 2, 3, we have c1, c2, c3, c4, right? So for first equation, coefficient of c1 is 1, others is 0. For second equation, coefficient of c1 is 1, c2 is also 1, and others is 0. For third equation, coefficient of c1 is 1, for c2 it's 2, then we have both 0. And then u for its c1 is, yeah, 1, c2 coefficient is 3, and then others is 0, right? So this here a is this is our matrix here, and in order to find c1, c2, c3, c4, we need to take the inverse of this matrix, right? So you can clearly see that the two columns of this matrix are directly 0. So no way this matrix is going to be invertible. So even if you look at these equations here, these equations, you can see that there are no terms of C3 and C4 coming. So it's impossible to find C3, a unique solution for C3 and C4, right? So that makes kind of solution impossible to exist, and hence there's no way we can find uh, the interpolation functions for such type of four-noded element, right? That can fit into this function here. So this is not possible, right? So this was just a demonstration or why we discussed earlier why this such type of elements are not possible. And then so if we need four nodes, then we need a four-noded element. We have to have them separate. So now this type of element would be suitable and would work properly without any numerical problems for this kind of interpolation function. Okay, I hope there's no doubt here. It's a pretty straightforward question. I just didn't wanted to make it more complicated. Just wanted need to demonstrate why this different types of any type of elements cannot work for such type of interpolation. Okay, so if this is there are no questions in this problem, we can move on to the next problem. So we're given different 3 by 3 matrices, and we have to see which have linearly independent rows and columns, right? So we discussed a similar problem earlier. I have taken this problem from the assignment. Uh, First thing is we can try to figure out if any rows and columns are linearly dependent or not. And the other thing is we can just go ahead with finding the determinant of the matrix. We can directly know if determinant is zero. We know that the rows or columns would must be linearly dependent, right? So we can see for option A first. Can someone tell me? Can someone answer this? I'll try to solve. So if we take add column 1 plus column 2, we get we have 2 3 7 plus 5 6 1. So we get 7 9 8, right? Which is equal to column 2. Sorry, it's not column 2, it's column 3. So we get column 2 here, right? So clearly this matrix has linearly independent rows and columns. Sorry, linearly dependent. So this is not the right answer. Then in the next problem we have, can we see if it's possible to see if the rows and columns are linearly dependent or not?
Sir, I think C will be the answer.
Okay, so yeah, C is the answer, right? I was just checking if other options would give us a correct answer or not. It's verifying. So C, yeah, you can verify this by taking the determinant of this here. So it's 2 times 81 minus 52 minus times 27 minus 24 plus 5 times 21 minus 36. So we get 51 minus, just save time using calculator. So 81 minus 42, 78 minus 7 minus 20 is 3 minus 7, 3 into minus 7 is minus 21. Then we have 21 minus 36 is minus 15 to 5 is minus 75. Yes. So we have 78 minus 21 minus 75, which is minus 80. Right? So this is not equal to 0. So hence C is of course the correct answer here. And if we try to look at the other options, B, I think B would also be correct. I'll just check. So we just check the determinant for B also. 2 times 32 minus 20 minus 3 times 8 plus 10 plus 5 times 2 plus 4. We get 32 minus 20, we get 12, 12 into 2, 24 minus 8 plus 10, 18, 18, 3, 54. Then we have 2 plus 4 is 6 plus into 5, 30. Right, so we have 24 plus 30 is 54. 54 minus 54 is 0. Yeah, this is also wrong. I think there was a discrepancy in the solution. So in the assignment given there it was plus 2 here. So in the solution they have given minus 2, so minus 2 would make it as a wrong answer, right? Okay, so again D will also be wrong answer. So we have the correct answer C, as rightly pointed out by sir. Okay, so I think we are out of time here, so we can stop the session. And if there's any doubts coming, the we can discuss the doubts now. Otherwise, if there are no doubts, you guys are free to sign off the session.
Oh, sir, yes. Thank you, sir. Thank you.
Thank you so much. Okay, so then we'll pack it up, and we'll meet in next week in this session where we discuss the content of week 6. Uh, so I welcome you all again. I thank you all again, and I welcome you. I hope to see you in the future session also. Thank you so much.
Okay, okay, sir.